Okay, we're going to look at Chapter 9 for Exam 5, do a little review based upon the review document. I've got several of them picked out, several questions here picked out. We're not, obviously not going to have time to do all of them, but I picked out the ones that I thought would be most relevant and cover all the topics. So let's get started with number 1. Consider that calcium metal reacts with oxygen gas in air to form calcium oxide. Okay, immediately you know you're going to have to write compounds and a balanced equation. Then we say, suppose we react. Let's see, is that red showing up? Because I have trouble seeing it on the video when I process the things. 5.66 moles of calcium and 4 moles of oxygen gas. Determine the number of moles of oxygen left over after the reaction is complete. Okay, we're going to jump right into the big middle of it right here, this first one. We're not going to take it slow today, apparently. So we write the balanced equation first. We're going to react calcium and oxygen, which has to be O2, otherwise it won't balance. Calcium and oxygen yields what? Calcium oxide. Okay, got to be sure to write these correctly. That's a no-brainer. This one might take some memory, right? Diatomic gas, and then calcium oxide. Calcium is an alkaline earth with a 2+ charge. Oxygen's a chalcogen with a -2 charge. So you just need one of each. Now to balance them, you need 2 oxygens. We don't even need to do the budget for this one. It's really simple. 2 oxygens, 2 calciums. So now you got a balanced equation. Now, what were we given? 5.66 moles of calcium. And how much oxygen? 4 moles of oxygen. Okay? Remember, whenever you're given exact amounts of reactants, you can assume that one of them is going to run out. It's very rare that you will have a stoichiometric mixture, especially in the real world, but even on test problems. So you've got to find out which one of these is limiting. Remember how we do that? We say, okay, we got a conversion factor that we need to draw for this one. This many moles of calcium. How many moles of calcium oxide will that produce? Well, that's one way to solve the problem. But the question is not calcium oxide, right? The question is, how many moles of oxygen are left over? So that assumes that oxygen is in excess, but I wouldn't take it at face value. Let's look at it this way. If we have this much calcium, how much oxygen is required? If we do it like that, then we can answer the question. Moles of oxygen, right? 1 and 2 calcium. Okay, so now the moles of calcium cancel. And what are you left with? 5.66 divided by 2. Let's see if I can do that in my head. Let's say 2, 8, and 3. Correct? That's how much oxygen is required, if I did that correctly. Let me check my math. 16. Yep, that's right. This is how much oxygen is required. So if you've got 4 moles of oxygen there, obviously there's plenty. And all of this is going to run out. So this one is limiting. Calcium is limiting. And you've got 4 moles of oxygen to start with. How much do you have left over? You just subtract that one from that one. 1.17. Let's see, check my math. That's how much remains. 1.17 moles of oxygen remain after this reaction is complete. All right. That wasn't as bad as I thought it was going to be. We just have to step through it methodically. All right, let's see. Let's take a look at number 3. Okay. Sodium and water react. That's an understatement. If you put pure sodium in water, you're going to get a reaction that's extremely violent, exothermic. Produces lots of heat. And hydrogen gas, which if there's enough heat, hydrogen gas in air will ignite from that heat. So this could be a catastrophic reaction. One thing I do know is my subscripts are not right. Right? That 2 right there should be a subscript. That 2 should be a subscript. And make myself a note in case it needs correction in other documents. But here's our working equation. And it's probably balanced. Let's check it out, see if it is balanced. Water yields sodium hydroxide plus hydrogen gas. Let's see. One of these, it says we need 2 of those. And it says we need 2 of these. So let's see. 2 sodiums, 2 sodiums. 4 hydrogens, 2 hydrogens here, 2 hydrogens there. We're good. 2 oxygens, 2 oxygens. Okay, so it is balanced. What number of moles of hydrogen will be produced when 4 moles of sodium is added to 1.2 moles of water? Okay, we're given both reactants in amounts, so one of them is going to run out. We have to decide which one runs out, and at the same time, efficiently answer the question. How many moles of hydrogen will be produced? In this case, we do want to say, if all this is consumed, how much hydrogen will it produce? And then we say, if all of this one is consumed, how much hydrogen is produced? Then compare the 2. The least amount is the limiting one, and that answers our question. So if we say 4 moles of sodium would give us how many moles of hydrogen? So there's 1 hydrogen for every 2 sodiums. That means 2 moles of hydrogen will be produced from this one. From this one, 1.2 moles of water. We want to convert that one to hydrogen. Oops. There we go. The ratio is 2 waters and 1 hydrogen. Okay, so that says 2 divided into 1.2 is 0.2. 6 moles of hydrogen. That means this one is limiting. And this one is excess. Okay. That means this is our answer. Right? What number of moles of hydrogen will be produced? That's it. Because once this is consumed, the reaction stops. There's not enough water to produce that many moles from sodium. So we have excess sodium left over after this reaction is complete. And that's why, let's see, I accidentally bumped the button. That's why the answer is 0.6 moles. Okay? All right, let's see. Mark the next one as number 5. Here we go. In this reaction, nitrogen plus hydrogen yields ammonia. How many moles of ammonia would be produced from 1.21 moles of hydrogen in excess nitrogen? Actually, this is a simpler equation, a simpler problem, because we're already told that there's excess nitrogen. Right? And is the equation balanced as given? Well, let's see. 6 hydrogens, 2 times 3 is 6 hydrogens, 2 nitrogens, it's balanced. What are we given? 1.21 moles of hydrogen and excess nitrogen. So all of this is going to be consumed. So it's really a simple unit conversion. So that's moles of hydrogen. We want to cancel moles of hydrogen. Oops. Wrong place. And leave us with ammonia. So we have 2 here, 3 there. Let's see. I'm going to use my calculator for this one. And I get 0.8, let's see, 3 significant figures. 0.807. 0.807 moles of ammonia. Does that answer our question? How many moles of ammonia? Okay, there it is right there. 0.807 moles of ammonia. All right, how about, number 6. Do number 6. Let's see, yeah, it's all there. All the answers are there, so I don't have to scroll. So, we're given this unbalanced equation, tells you right there. That's the first thing you're going to have to do is balance that equation. If 1.7 grams of ethanol react with 11.2 grams of oxygen, that's ethanol right there. That's oxygen. How many moles of carbon dioxide are produced? Okay. This one is also going to be a process of determining the limiting reactant, because we want to find out how much product carbon dioxide is produced. All right, let's put the equation up there and balance it first. Okay. So with something this big, maybe you want to use the budget, use the method, and balance this equation. So let's see, did I write it correctly? Here, there, right? Because if I don't write those things correctly, it'll never balance. So we've got carbon, hydrogen, and oxygen. That's it. 2 carbons, 5, 6 hydrogens, and 1 2, 3 oxygens to begin with. On this side, we have 1 carbon, 2 hydrogens, and 1, 2, 3 oxygens. Okay? We do have an element here, so we want to hold that one till last. Don't balance the oxygens till the very end. And as it turns out, they're already balanced, but I'm pretty sure that's going to change. Carbons. If we need 2 carbons here, that coefficient will give us 2 carbons, but it'll also give us 5 oxygens. Okay? How about hydrogens? All right, we have 6 hydrogens here. We have 2 here, so a 3 will give us 6 hydrogens. But it'll also add 3 oxygens. So 3 plus 4 is 7. Okay? Now, we've got 7 oxygens here, 3 here. The oxygens are in 2 locations. And we want a coefficient here that will balance that 7. Right? We've already accounted for 1. 1 oxygen is covered. So we really only need to have 6 oxygens out of this term. So if we put a 3 here, that's 6 plus 1 is 7. Okay? And our equation is balanced. Now we can answer the question. With that balanced equation, what are we given? 1.7 grams of ethanol. Okay? And 11.2 grams of oxygen. All right. So remember, you can't go anywhere in a balanced equation unless you have moles. Right? We've got grams. We need to make moles. So how do you make moles out of grams? The molar mass of the compound or the element. In this case, we have 2 carbons, 5 hydrogens, 6 hydrogens, and 1 oxygen. So we need 2 times 12.01. That's for the carbons. We have 6 hydrogens, which is 1.01. This is grams per mole. And then we have 1 oxygen. 16. Look those up in your periodic table. You'll see that that's true. And I must have punched a button again. There we go. All right. So what's that total? I'm going to use my calculator again. So 12.01 times 2 and 6.06 plus, and then 16 plus. So I'll get 46.08 grams per mole. Now we can convert this one. 1.70 grams. We want to convert that. Grams on the bottom, moles on the top. So this grams goes on the bottom. That way we can cancel the grams and calculate our moles. 1.7 divided by that number is 3.69 times 10 to the minus 2 moles of ethanol. That's my abbreviation for ethanol. I keep the OH on there because it's an alcohol. And this is the ethan part, ethanol. Okay, how many moles of this one are produced? Well, let's see. This one should be easier because we know the molar mass of oxygen is 2 times 16. So it's 32 grams here and 1 mole there. Right? So 11.2 divided by 32 is 3.50 times 10 to the minus 1 moles of oxygen. Okay, now that we know the moles of each of our compounds, we can determine which one is limiting. Since the problem asks us about moles of carbon dioxide, let's convert this into moles of carbon dioxide and convert this one into moles of carbon dioxide and see which one is the smaller. So if we have 3.50 times 10 to the minus 1 moles of oxygen, we need a conversion factor to get rid of oxygen and leave us with carbon dioxide. Coefficient for carbon dioxide is 2, and for oxygen is 3. So I need to take that last number and take 2/3 of it, which is 2.33 times 10 to the minus 1 moles of carbon dioxide. That's produced from oxygen. From ethanol, 3.69 times 10 to the minus 2. Let's see. Let's be consistent. Moles of ethanol. Now we want to convert that. So ethanol and CO2. So the coefficient in front of ethanol is 1 and 2 in front of carbon dioxide. So 2 times that value is 7.38 times 10 to the minus 2 moles of CO2. Okay, now we can compare these two. This one is the smaller amount, correct? So that's the limiting one. This is the amount of carbon dioxide that will be produced. So how about our answers? Well, they're in standard notation. So we know this is the one we want. Converted to standard notation. Right? 7, 3, 8. Right? Move it 2 to the left. Here, 1, 2. We don't need that one. So that's how many moles of carbon dioxide will be produced. And here it is right here, 0.0738 moles. Okay? Those types of problems require very methodical procedure. In other words, you must have worked problems like this before until you can do them in your sleep. You know the steps, and you have to do the steps in sequence without mistakes in order to arrive at the answer. All right, that was 6, 7. Okay. Fe2O3, what is that? Right. Iron is a transition metal. It's going to have multiple charges. So we have to name it with a Roman numeral. So what's the Roman numeral? The charge of the iron? Well, if oxygen is -2, 3 times that is -6. So the iron has to cover a -6 charge with a +6. But we have 2 irons, so each one is +3. So that's iron 3 oxide. Okay, this iron 3 oxide, and you're given the molar mass, so you don't have to waste time calculating that in case you need it, reacts with carbon monoxide according to this equation. And it appears to be balanced. Let's see, 2 irons, 2 irons, 3 plus 3 is 6 oxygens, 6 oxygens, 3 carbons, 3 carbons. It is balanced. Right, so let's write that equation up here. Fe2O3 plus 3 carbon monoxide yields 3 carbon dioxide plus 2 iron. All right, so we're given 185.5 grams of carbon monoxide. 185.5 grams of carbon monoxide react with excess Fe2O3. How many moles of iron will be produced? All right, we know that if this is excess, then all of this is going to yield that. So what we have to do is convert this to moles, because we can't go anywhere in this equation without moles. Grams won't do it. So we're going to convert that to moles of carbon dioxide. Okay, and we're given the conversion factor right here. Excuse me, carbon monoxide. Carbon monoxide converted to moles of carbon monoxide. 28 grams per mole. Okay? So we could do this all in one step. Right? If I do this calculation, 185.5, and then divide by 28, I get 6.625 moles of carbon monoxide. And then we take 6.625 moles of carbon monoxide and convert it to iron. Okay? So the coefficient of iron is 2, and the carbon monoxide is 3. So we just take 2/3 of that value, and I get 4 significant figures, 4.417 of iron. The best answer out of this one is that right there, 4.415. We don't have a selection there that says none of the above. So that's the best answer. We could have done this all in one step. All we would have had to do was, notice that that's canceled. So now that's moles of, this is moles of carbon monoxide. Then we could have used this conversion factor on the tail end of that one and done that whole calculation in one step. But this way you understand this part and then that part. We treat them separately. It works the same way. All right, that was 7. Now let's get down to number 10. There it is. Okay, refer to the following equation. Looks like it's balanced. Let's see. 4 nitrogens. Yep, 4 nitrogens. Let's see, 12 hydrogens. 2 times 6 is 12 hydrogens. There you go. 14 oxygens. So we have 8 oxygens here and 6 oxygens there. 14 oxygens. We're balanced. How many moles of ammonia would be required to produce 11.9 moles of water? Okay, this is actually simpler than the ones we've been doing. So we have 4 ammonias plus 7 oxygens yield 4 nitrogen dioxide and 6 water. And what are we given? 11.9 moles of water are produced. And the question is, how many moles of ammonia are required? Okay, how many moles of ammonia? Now, in this one, we have to assume that oxygen is in excess. We got plenty of it. So we just use the coefficients as a conversion factor. 11.9 moles of water will be produced from how many moles of ammonia? Right? Cancel waters, leaves you with ammonia. So we have 6 coefficient here for water and 4 here for ammonia. So there we have 4/6 or 2/3 multiplied by 11.9. I get 3 significant figures, 7.93. Right, these cancel, leaves us with ammonia. 7.93 right here. All right, that was 10. Let's look at number 13. All right, 13. Scroll down, see if I can catch it. I'm gonna have to do it the hard way. Okay. There's 13. Consider the following unbalanced equation. Right? There's a clue right there. You're going to have to balance this thing. If 3.09 moles of silicon were produced, how many moles of sodium fluoride were reacted? Were also created. Okay. So we need to balance this equation. Sodium silicon fluoride. That's 6. Yes. 6. Plus sodium yields silicon plus sodium fluoride. Okay, so let's balance it. We could probably do this without the budget. But let's do the budget anyway. Sodium, silicon, fluorine. Okay, we have 3 sodiums, 1 silicon, and 6 fluorines. And over here we have 1 sodium, 1 silicon, 1 fluorine. Okay, we've got a sodium here, metal. We've also got a sodium element, silicon element here. So we could do either one last. I'm thinking that we probably want to do sodium last because it's in 2 places. And we'll get the silicon before that. But let's look at the fluorines. We need 6 fluorines, right? 6 fluorines. So now we can do silicon. Well, silicon's already balanced. So let's leave it alone. See if we can balance the sodiums. Right? We have 6 Right, 6 fluorine, 6 sodiums. Yeah, I forgot that part. 6 sodiums, 6 fluorine, 1 silicon. Okay, how do we get 6 sodiums out of this one? You've already got 2. Right? So you only need 4 more. So 4 plus 2 is 6. And we're balanced. All right, now that we have a balanced equation, what else are we given? 3.09 moles of silicon are produced. Okay, and the question is, how many moles of sodium fluoride were produced? How many moles of this one? Okay. What do we need? coefficients. Silicon is 1, 6 here. All right, so we just need 6 times 3.09. Maybe I can do that when I get 54, 5, 18. Right? 18 moles of sodium chloride. Yeah, that's got more significant figures than I should have. So rounded off, it's 18.5. Rounded off, 18.5 moles of silicon fluoride, sodium fluoride are produced. Also, in addition to the silicon. All right, that's 13. Let's see. Next one I have marked is 18. There it is. How many atoms of aluminum can be produced by the decomposition of 31.5 grams of aluminum oxide? It can give you a hint. Write the balanced equation. Decompose aluminum oxide. What is a decomposition reaction? It's one in which a compound produces elements, right? So if this decomposes, how many alumins are it going to produce? 2. How many oxygens are you going to produce? Well, let's say that's not true, right? I'm jumping the gun. First, we got to write the correct elements, or, well, in this case, elements. Oxygen is going to be diatomic, correct? Right. So now, how do we get an even and an odd to behave? Cross multiply. 3 times this one and 2 times this one will give you 6 oxygens each. It'll also give you 4 aluminum. Right. So check me, is that balanced? We could have gone about it a different way, but this was the quickest way. 4 aluminums, 6 oxygens, we're balanced. Now that we have a balanced equation, we can answer the question. 31.5 grams of aluminum oxide. 31.5 grams of aluminum oxide. And the question is, how many atoms of aluminum? So first of all, we're going to need to know moles. Right? Because this has no relationship to atoms except through moles. So we need to convert this one to moles like that, which means what? Molar mass. So we have to calculate the molar mass of aluminum oxide. So we go to our periodic table. Aluminum is 26.98. 26.98 times 2. And then 3 oxygens. So let's see what that value is. 26.98 times 2. And then what's 3 times 16? I think it's 48. So that's 101.96. 101.96 grams per mole. So 101.96 goes here, so we can cancel the grams and leave us with moles. We're going to divide that number into that number. And I get 0.308. Let's keep a decimal for now, so we can avoid rounding errors. So that's how many moles of aluminum oxide. Now, how many moles of aluminum are produced? We need a conversion factor. We need a conversion factor for this one. And if we convert this many moles to moles of aluminum, we need aluminum on top and aluminum oxide on the bottom. And the coefficient for aluminum oxide is 2, coefficient for aluminum is 4. So we just need to double that number. And I get 0.6179 moles of aluminum. Now we can convert to atoms, right? And what's the magic number for atoms? Avogadro's number. Okay, so that number 6.022 times 10 to the 23rd multiplied by this one gives us, now I can round it off, 3 significant figures. 3.72 times 10 to the 23rd atoms. Okay, there it is right there. There's no way that you can do this calculation in a split second. You've got to do it methodically. Balance the equation. What do you know? Where are you headed? How do you get there? Well, you can't go straight from grams to atoms, so you have to go through another numerical conversion. Convert mass to moles. Then you convert moles to moles of your target aluminum. Then you convert to atoms. So it's a step-by-step process. You can't skip any of those steps. There's no quick way to get there. All right, that was 18. Now I'm going to skip down to 23. There we go. 23. Calculate the mass of water produced when 9.47 grams of methane here reacts with an excess of oxygen in this following unbalanced equation. So there's your clue. It's unbalanced. We have to balance it. So here's methane plus oxygen yields carbon dioxide and water. Balance the equation. All right, let's set up our budget. Carbon, hydrogen, oxygen. So we have 1 carbon here, 4 hydrogens, 2 oxygens. We got 1 carbon here, 2 hydrogens, and 3 oxygens. Okay? So we're going to save oxygen till last. And we're going to go for, carbons are already balanced. Let's go for hydrogen next. So we need 4 hydrogens. That gives us now 2 plus 2 is 4 oxygens. All right. So we can balance the oxygens with a coefficient of 2. There you go. Now we're balanced. Now we can put in the information that's given. 9.47 grams of methane and an excess oxygen. 9.47 grams. This is excess. Okay. Now the question is the mass of water. So we want to know what's the mass of that water. Okay. Same as always. You can't get there with this value. You have to have moles because the ratio of these reactants and products is numbers of moles. That's what those coefficients mean. 2 moles of water, 1 mole of carbon dioxide are produced from 2 moles of oxygen and 1 mole of methane. So we got to convert this one to moles. Okay, what's the molar mass of methane? Well, it's 12.01 and 4 hydrogens, 4.04. I get 16.05. There we go. Divide that into this value. .590. That's moles of methane. So now we need to convert that to moles of water. So we have a 2 coefficient here and a 1 there. So just 2 times that value. I get 1.18 moles of water. Now we need to convert that to mass. Okay. What's the molar mass of water? We've done that several times. Add them up, you get an 18.02. Okay, 18.02 times that value. And I get 3 significant figures. 21.3 grams of water. Right here. 21.3 grams. Okay. All right, let's see. Let's skip down to 26. Gotta scroll that one. There we go. Okay. Consider the unbalanced equation. There we go again. We have to balance this equation. How many moles of water are needed to react with 206 grams? What is that? Aluminum carbide. All right. Where would you find aluminum carbide in the real world? Go to any hardware store and pick up a piece of sandpaper. It's probably got aluminum carbide on it. Maybe, it depends. It's a specialty paper, right? You need something that's very hard for grinding. Most often they have aluminum oxide. It's a lot cheaper. But if you need something that's really hard, aluminum carbide is a good choice. Okay, let's get back to the problem. Al4C3 and water produce aluminum hydroxide. Is that right? Aluminum is always +3. Polyatomic ion -1, they're balanced. And methane. All right, so let's balance this equation. Notice that there's a polyatomic here, but it's not on both sides, right? So we can't use that as a balancing group. We have to use individual elements. So we got aluminum, we got carbon, hydrogen, and oxygen. So let's tally them up. 4, 3 carbons, hydrogens, only 2 of them, and 1 oxygen. Let's see, 7, 8, 9, 10. 4, 5, 6, 7, 8, 9, 10. Okay. Aluminum, 1. Carbon, 1. Hydrogen, 4 plus 3. 7 hydrogens. Oxygens, 3 oxygens. Okay. That's our starting point. All right, let's see. We don't have any elements here, so we can't hold elements out. Next best thing is we usually hold water. So let's see. If we start with aluminums, right, we need 4 of them. That's a 4 there. But that also changes the number of oxygens. So we have 3 times 4 is 12. 12 oxygens. And 3 times 4 is 12 hydrogens. Oops. 12 plus 4 is 16. Right? Let's see. 3 times 4 is 12. Yes. 16 hydrogens. Okay. We got aluminums. Okay. All covered. That's good. Now, what if we do carbons? Well, we need 3 carbons. Okay. But that gives us 12 hydrogens. And over here, we still got 12, so that's 24 hydrogens. Okay. That didn't change anything else but carbons and hydrogens. Okay. That one's good, that one's good. These two, we still need to balance hydrogens and oxygens on this side. These hydrogen and oxygens, if we have 8 here, no, that's not right. Hold on a second. That's not right. 3 times 4 is 12 oxygens. Oh, 3 times 4 is 12 hydrogens. And then 3 times 4 is 12. It's 24 hydrogens. This is 24. And the oxygens are 3 times 4 is 12. That's only 12. And nobody stopped me. So how do I know how did I know to stop and check that? Because I knew that I couldn't multiply this by any coefficient and give me those values. So I went back and checked it, and I had made a mistake. So retally. Now, if I want 24 hydrogens, or if I want 12 oxygens, I need a 12 here, and 2 times 12 is 24. Now it balances. Okay? If I can't balance it, then I'm stuck. I can't go anywhere. Can't do anything with it. But now that it balances, we're ready to go to the next step. All right. So now what are we given? 206 grams of aluminum carbide. All right. And the question is, how many moles of water are needed? So the question here is moles of water. Right? So this, we know this is going to have to be converted to moles. That's the only way to go anywhere in this equation. So we need 206 grams moles. So what's the molar mass of this compound? Well, we need to go back and look at aluminum again. 26.98. 26.98 times 4. And then 3 times carbon. Right. So let's do that calculation. I get 143.95. grams per mole. So this one's going on the bottom. I have to cancel grams. Now we divide 206 by that number. And I get, let's see, three significant figures. 1.43 moles of aluminum carbide. Now we want to convert it to moles of water. So let's just do it like this. Notice I've been leaving out the moles here because the moles cancel anyway. And this is water. So what are the coefficients? 1 here and 12 there. So I need 12 times that number. 17.2 moles of water. Let's see, do we have any close there? Yeah, there's one. 17.2 moles of water. All right. So, except for my mistake, that was pretty straightforward. You're always asking yourself, is what I'm doing make sense? Not just at the end, but for each step. Does it make sense? I caught myself in an error. Let's see, 29. Let me scroll that up a little bit. All right. So here's an interesting problem. We've got for 29, we've got this reaction, but there's an unknown element here. 6 X's plus 2 diboron trioxide. 6 X's plus 2 diboron trioxide yields B4X3 plus 3XO2. Okay, so we've got X's in 3 positions here. And the question is, what is X? Okay, so work backwards from the question. How do we determine an element? An unknown element, what do we need to find that element? We have 2 choices. If you know the number of protons, the atomic number, it's simple. You just look on the periodic table, and they're ordered from left to right, top to bottom in atomic numbers. I mean, they're whole numbers. Hydrogen's 1, helium's 2, lithium's 3, beryllium's 4. You just keep going until you find the right one. But we don't have enough information here to do that, right? Nothing in here will tell us the number of protons. So the next best thing is molar mass, because molar masses also increase from left to right, top to bottom. They're not neat whole numbers, but most of them are unique for the element. Only in a couple of places are the molar masses so close together for neighboring elements that you need some sort of tiebreaker. But that's our only choice. We don't have any other choice. So how do you do molar mass? Well, you need molar mass, or molecular weight. That's the way I abbreviate it. You need mass per moles. Right? Do we have mass? Right? It says 165 grams of X. We do have mass. What we need is moles. We need to find out how many moles of X are represented by that many grams. So what does it produce? Well, in the reaction, 165 grams of this reacts completely with diboron trioxide to produce 2.29 moles of B4X3. 2.29 moles, 2.29 moles. Okay, so we know how many moles of this is produced. This arc produced. Can we find out how many moles of this? Well, yeah. If you have moles of a reactant or a product, you can find out the number of moles of any other component, reactants or products. So if we have 2.29 moles of B4X3, we want to convert that to moles of X. Right? What's the ratio? Well, first of all, is this a balanced equation? 6 X's, 3 plus 3 is 6 X's, 4 borons, and 6 oxygens, 6 oxygens. So it's balanced. I needed to confirm that for myself. Now that we know it's balanced, we can use the coefficients. So there's a 1 there, and there's a 6 here. So 6 times that value, 2.29, is 13.74. That's how many moles of X there are. 13.74 moles. So now we can calculate the molar mass. 165 grams divided by that number. And I get 12.01 grams per mole. That's the molar mass of the element. So you go to your periodic table and look, start at the top, go from left to right, down the periods until you find 12.01. And by now you probably should have that one memorized. 12.01 is the molar mass for carbon. So X is carbon. Oops, wrong place. Here, carbon. Okay. Let's see, let's go to 32. How are we doing on time? I think we're pretty good. Be sure I don't miss any. 32 would be okay, 32. Okay, let's see if I can. There we go. Which of the following reaction mixtures would produce the greatest amount of product? Assuming all the reaction goes to completion. Each involves this reaction. Okay, so what are our choices? The first one is, let's see, A, B, C, D, and E. Right. This looks like an assembly line question. We got to compare each one of these to find out which one produces the greatest amount of ammonia. So we have 1 mole. Let's see, are they all moles? All moles, moles, moles. Yeah, they're all moles. So we have 1 mole of ammonia and 3 moles of hydrogen. And B, we have 5 moles of nitrogen and 3 moles of hydrogen. C, we have all would produce the same. Okay, same. And 1 mole and 6 moles. And 3 moles and 3 moles. Which would produce the greatest amount of ammonia. Okay? So with this many moles, how much of that would be produced? Which one is limiting? This is a stoichiometric mixture, 1 to 3, 1 to 3. Okay? So that means they would produce 2 moles of ammonia. How about this one? Well, you've got 3 moles here. You only need 1 nitrogen, right? You only need 1 mole of nitrogen. All of these are going to be consumed, and they'll produce 3 to 2. Okay? How about this one? You've got 1 of these and 6 of these. Which one runs out? Well, after 1 is used up, you've only used 3 of these. So that means nitrogen runs out and produces 2 moles of ammonia. Here's 3 to 3. You got 3 of these and 3 of those, but you only need 1 of these. So this one would also produce 2. So there's your answer. They're all the same. Okay? All right, that was 32. 33. Okay, it's all the answers are on the board right here. Balanced equation. A balanced equation, P4 6H2 produces pH3. Okay. Let's see. That looks to be balanced, yes. 5 moles of hydrogen. 5 moles is given. Would do what? Reacts with how many moles of P4? Well, to answer this question, right, A is just dumb. Right? It will react because we've got a balanced equation for it. Cannot react with phosphorus? No, it will. Reacts with how many moles of P4? So A is just dumb. B, how many moles of P4 will that react with? Well, 6 of these for every one of those. So 5, and this is hydrogen. So hydrogen, P4, and we have 6 and 1. So 5/6. Let's see, 6 into 5. 6 into 5. 0.83. 0.83 of P4. All right. Is that true? No. That was false. How about C? Produces 3.3 moles of pH3. So if we have 6, we still have 5 moles of hydrogen. pH3, how many pH3 moles were produced? We have 4 here and 6 there. So 2/3 of 5. Is 3.33. We have 2 significant figures, moles of pH3. That's true. We found our answer. right? And we don't have any in here. That was just dumb. We don't have any in here that say 2 of the above or none of the above. And that, so once you find your answer, in the interest of time, it's probably good for you to move on. D and E would be false. All right, 33. Let's see, what's next on my list? 39. And everything's there. We'll look at 39. Consider the reaction of magnesium metal with hydrochloric acid. Magnesium metal, right, plus hydrochloric acid, which means aqueous. To produce magnesium chloride, let's write that one correctly. Magnesium is an alkaline earth, it's 2+ charge. Halogens are -1, so we need 2 of them. Magnesium chloride, let's see, and hydrogen gas. All right, and this is aqueous. Okay, so we have our equation. Now we need to balance it before we can answer the question, right? Because how many moles of hydrogen gas are produced, right? If we're given this many moles of magnesium and that many moles of hydrochloric acid, then we need a balanced equation. So can we do this in our heads? Well, you got 2 hydrogens here. We need 2 hydrogens there. But that gives us 2 chlorine. We've got 2 chlorine, 1 magnesium, 1 magnesium. That was done. We didn't even have to do the budget. Now what are we given? 4.52 moles of magnesium and 4.52 moles of hydrochloric acid. Okay. How many moles of hydrogen gas are produced? We've got given amounts of both reactants. One of them is going to run out. We just need to know which one. We could go ahead and do the calculation, you know, say how much of what, how much of what, and that would give us our answer. Or we could say, how many moles of this, how many moles of this are required to react with that? Well, only half of those are going to react. Right, so this one is the limiting reactant. But since we're going for an answer, we can do it the old-fashioned way. We can say 4.52 moles of magnesium would produce how many moles of hydrogen? Right? The ratio is 1 to 1. So that would produce 4.52 moles of hydrogen gas. How about this one? This is HCl, so we need HCl here and hydrogen gas there. This one's 2 and that's 1. So half of that would be, let's see, 2.26, 16, 4, 5, yeah, moles of hydrogen. So this is the limiting one. And this is excess. So this is how much hydrogen is produced, 2.26 moles here. Okay? Let's see. 43. Okay, scroll down. As luck would have it, I do it the hard way. There we go. So this question is based upon this balanced equation. I'm pretty sure it's balanced because of those coefficients. So we can check it out. 4 nitrogens, yep. 12 hydrogens, yep. And 14 oxygens. So 8 plus 6 is 14. Didn't we balance this equation before? Maybe not. Anyway, how many moles of water are produced if 9.12 moles of NO2 is given off? So for this balanced equation, H3 plus O2 yields NO2 plus 6 water. That's 4, that's 7, and this is 4. Okay, what do we get them? 9.12 moles of NO2 are given off as a gas. The question is, how many moles of water are produced? So along with this many moles of gas, how many moles of water are produced? Oops, how many molecules of water are produced? Okay, we still have to do moles. So what's the ratio here? 4.12 moles of NO2 converted to water. That's 6 here and 4 there. So 4.12 times 6 divided by 4 is 6.18. Moles of water, right? So we need to make another calculation for molecules of water. And what's the magic number? Moles, molecules. 6.022 times 10 to the 23rd. Times that value. Let's see, round it off to 3 significant figures. 3.72. 10 to the 24th molecules of water. Hold on a second. What did I do wrong? Oh. See what I did wrong? I started off with the wrong number. That's a 9. Right? So this is going to be wrong. That's wrong. And this is wrong. Let's do it again. 9.12. That's 13.68. Now times Avogadro's number. 8.24. There we go. All right, that was 43. And 45. There we go. Tin-2 fluoride is added to some dental products to help prevent cavities. Right? That's how they get the fluorine in your toothpaste. Manufacturers have to make the tin-2 fluoride first, though, before they can add it to their products. So they take tin metal, hydrofluoric acid, and that makes tin-2 fluoride plus hydrogen gas. How many grams of tin-2 fluoride can be made from 49.6 grams of hydrogen fluoride if there's plenty of tin? So 10 is the excess. We're given the balanced equation. That was nice of them. And hydrofluoric acid yields 10,2 fluoride and hydrogen gas. Let's see. Two of these. Let's see, that's 2 hydrogens, 2 fluorines, 110. We're balanced. Okay, so what are we given? 49.6 grams of hydrogen fluoride. And 10 is excess. Right? Now the question is, how many grams of 10,2 fluoride are produced? Okay, now we have a balanced equation, we have information that's given, and we know the question. So in order to get from here to here, this has to be converted to moles. Okay, what's the molar mass of hydrofluoric acid? Well, let's see. 19.00 for fluorine. And then hydrogen is 1.01. So that's 20.01. Divided into 49.6, which is 2.479. 479 moles of HF. Now we need to convert that to moles of 10,2 fluoride. And the magic numbers are 2 and 1. So we divide that by 2. And I get 1.239. 1.239 moles of that compound. Now the question is, how many grams? Right. So we got to convert it back. So 1.239, and I'm hanging on to an extra decimal so we can avoid rounding errors. Molar mass. This time moles on the bottom and grams on the top. But it's a different compound. So we have to say, how much does 10 weigh? 118.71. 118.71 for 10. And then 2 fluorines. Fluorine is 19. We just determined that one. So 2 of those is 38. That means 156.71. Okay. Times 1.239. And I get, let me do that again. That doesn't look right. 156.71. There we go. So I get 194 points. Let's see. 3 significant figures. 194. Grams of 10,2 fluoride. Okay? Right here. All right, so that was 45. Next. Skip on down to 60. Okay. There it is, 60. Consider the following reaction. We have to assume that this is balanced. 2 A's plus 1 B yields 3 C's plus 1 D. So let's put that up there. 2 A's plus 1 B yields 3 C's plus 1 D. Now we're also given 3.35 moles of A. Okay? And 2 moles of B. All right? React to form 4 moles of C. Okay? What's the percent yield? Remember, how do you calculate percent yield? You have the actual yield of a product, in this case, C, divided by the theoretical yield, that is the stoichiometric yield of that same product. So you divide that into the actual times 100. And what we did in class last week, we used mass as our ratio. We don't have that here. All we have is moles, and there's no way to get mass because we don't know the molar mass of A, B, C, or D. So we just have to calculate it. To answer the question, we've got to calculate it based on what we have, which is moles. So what you need is percent yield. In this case, will be actual C divided by theoretical C times 100 in moles. So we're given that this moles plus that moles yields that moles. This is the actual moles of C. So it's 4 moles of C divided by, what's the theoretical? The theoretical requires us to use this information to calculate it. So the ratio here is, let's see, 3.35 moles of A. We want to convert to C. A, C. C is 3, A is 2. So 3 halves of A, 3.35, 3 times, and then 2 divided is 5.03. But we still have to find out which one's limiting. So let's say 2 moles of B. Convert B into C. So it's still 3B, 3 C's, but it's only 1 B. So 3 times this is 6. Right? Now we know which one's limiting. This one is limiting. The stoichiometric, the theoretical amount of C is 5.03. It can't be any higher than that. That's the maximum. 100% conversion. So that one goes right here. Times 100. So what do we get from that? 4 divided by 5.03. Oops. 5.03. I get, let's see, 3 significant figures. 79.5%. The best one, the closest one here is 79.6. Okay, so that's what you would put as your answer. Always give me the best answer. And if there's one in there that says none of the above, in that case, you would put none of the above. And if I marked it wrong, then you come to me and say, this is what I got. You show me your work. Or you put it up, put your work on your test, and I can see where you did your calculations correctly and you came up with none of the above. Then you get the credit, of course. You've proven your point. Okay, that was 60. How about 61? Oops. Yeah, we're gonna have to scroll that one. There we go. All right, calculate the molecules of oxygen required to react with 25 grams of sulfur in the following reaction. The molecules of oxygen. So we've got 2 sulfurs and 3 oxygens. Yield what? 2 sulfur trioxide. What type of reaction is that? It's a synthesis. You're making a compound out of elements. Okay, we're given 25 grams of sulfur. 25 grams. How many, calculate the molecules of oxygen required, right? So we're not saying oxygen's excess, we're just saying how many would be required if there's plenty available. So we want molecules. Molecules of oxygen. That implies that we want to know how many of these O2s are required. So 25.0 grams of sulfur, how many moles is that? Sulfur is 32.07. So 25 divided by 3207. And I get 7.795, well, 0.7795. 0.7795, did I say? That's moles of sulfur. 7795. That's right. Okay. Now we have to convert that into moles of oxygen. Right? The ratio is 3:2. So 3 times divided by 2 is 1.169 moles of oxygen. Now to find molecules, we need Avogadro's number. Right? 6.022 times 10 to the 23rd times that value. And I get 7.04 rounded off to 3 significant figures. 704 times 10 to the 23rd. Molecules of oxygen. There it is right there. And of course, the answer gives you a clue also. We're not asking for how many oxygen atoms, we're asking for how many molecules of O2. Right? So that's as far as you need to go. All right, 61. Let's skip down to 69. We cut it close. Out of time, get close out of time. 9:40. Okay, I may go over a few more minutes. If you have to go, that's fine. What did I say? 69 is next. Oops, I'm gonna have to scroll that one. Okay. 69. In the reaction between carbon monoxide and Fe3O4, this is an odd compound, Fe3O4. Why do I say that?
Well, Fe3O4. If oxygen is 2 minus, that means that 8 minus
Has to be balanced, right?
How are you going to get 8 out of 3 irons?
You can't. It's a fractional oxidation state.
But it is a real compound.
That's why it was given to you like this, so that you don't have to guess about its composition. That is the compound. The theoretical yield in the experiment is calculated as 47.2 grams of iron.
So it's going to produce iron at 47.2 grams actual.
Oh, no, I'm sorry. That's theoretical. Theoretical. When a careless chemistry student carries out the experiment, the actual yield is 37 grams.
Okay, this is actual.
In this case, we don't even need to know the balanced equation. We're given the information. This is the theoretical, this is the actual calculated percent yield.
So it's really simple. Just what does the equation say? 37 divided by 47.2 times 100.
Right. And we should get, is that D? Yeah, I better check it. Yeah, 78.4. That's it. That's D. Okay, that's the yield. Whoops. Oh. Emergency. I forgot to plug this thing in. The battery's about to run out. There we go. Yep, not yet. Hold on a second. There. Let's see, I moved it around some, so let me reposition. There we go. Okay. That was 69. And 70. 70? Oops. I really need a remote mouse. There we go. 70. 3.1 mole sample of KClO3, potassium chlorate, was decomposed according to this equation.
So 2 potassium chlorates decomposes to make 2 KCl's and 3 O2s. How many moles of O2 are formed? Assuming 100% yield. So with 3.1 mole this, we want to know moles of that, correct? It's simple. KClO3, O2, this is 3, that's 2.
So 3 halves of 3.1. 4.65.
Rounded off, 4.7 moles of O2.
There it is. Okay.
That was 70.
We ought to be getting close to the end. Let me see how many more I got. Yeah, I got several marked off. Okay. So if you have to go, go ahead. 71. Let me see if this is a repetition. 3.4 moles of iron react with chlorine according to this equation. How many moles of chlorine are required? We've done one like that before. So I'm going to skip 71 and look at 72. Ammonia reacts with oxygen to form nitrogen dioxide in water according to the following reaction. If you react with ammonia and oxygen at the end of the experiment, you find that you produce 23 grams of water and 8.52 grams of ammonia left over. Determine the mass of oxygen reacted. We've done one of these also. The equation's already balanced. We're given 23 grams of water at the end of the experiment and 8.52 grams of ammonia left over. What's the mass of oxygen? Maybe we better do this one. 72. This one could be complicated. So we've got 4 ammonias and 7 oxygens yields 4 nitrogen dioxide and 6 waters. 23 grams of water are produced. And you have 8.52 grams of ammonia left over. 8.52 grams in excess. So we had more than that to begin with to produce this. Determine the mass of oxygen reacted. We actually don't need that. If we're going to go from here to here, all we need is to convert 23 grams of water to moles, like that. And that's 1.276 moles of water. And then we convert that to moles of oxygen. So we need oxygen here, water here to cancel. And that's 6 waters, 7 oxygens. So 7 times 6 divide 1.489 moles of oxygen. Now we just need to convert this back to grams. Okay. Moles cancel. Oxygen. 2 times 16, 32. And rounded off to 3 significant figures. 47.7. Okay, there it is, 47.7 grams. What this problem did was it threw in your face a lot of blue smoke. Right? It told you that this was left over, but you don't need to know that. That's superfluous. All you needed was to convert that to moles, moles back to grams. You're done. That was 72. Let's see about 73. 73, we've done that type before. So I'm going to move to 75. See, have we done 75 before? Consider the following unbalanced equation. I forgot to silence my phone. Here we go. We balanced that equation before, and then if 1.86 grams of ethanol react with 14.3 grams of oxygen, how many moles of water produced? That is a limiting reactant problem. So you just need to balance the equation for 75, convert to moles, and which one is limiting? Then you can determine the moles of water produced. So I'm not going to do 75 either. We've done one like that already. How about 80? We're going to scroll 80. Let's see. 22.5 grams of nitrogen, 22.5 grams of hydrogen. Determine the mass of ammonia that can be produced from these two reactants. All right, for this one, it tells you the reactants, nitrogen gas and hydrogen gas, both diatomic, and it yields, it says, determine the mass of ammonia that can be produced from these. All right, that's it. You just need to balance the equation. Okay, then you go to the mass of ammonia that can be produced from this given amount, 22.5 grams here and 22.5 grams here. All right. In order to do this, we've got to convert to moles for each one of these. So for nitrogen, what's the molar mass of nitrogen? 14.01 times 2, 28.02. So that'll be the moles of nitrogen. Moles of hydrogen would be 2.02 grams per mole. Okay, so now we can do those calculations, find out how many moles of each reactant we're given. .803 moles of nitrogen. And divided by 2.02, 11.1 moles of hydrogen. So how many moles of ammonia can be produced from each one? Hydrogen, nitrogen, ammonia, ammonia. So that's 3 here and 2 here. And that one is 1 here and 2 here. Right? So this moles is, let's see, 0.803 times 2 is 1.61 of ammonia. And this one is 11.1, enter, 2 times 3 divided. This one's 7.4. So now we know which one's limiting. This one's limiting. And this is the number of moles that will actually be produced. So what was the question? The mass of ammonia. So now that we know the moles of ammonia, we can convert it to mass. Grams per mole of ammonia. 14.01 for nitrogen and 3.03 for the hydrogens because we have 3 of them. 3 times 1.01. That's 17.04 times 1.61 is 27.4 of ammonia. Okay, right here. That was 80. All right, let's see, how many more do I have? 2 more, let's see, 83. Have we done one like 83? Mp2O3 reacts with CO when 470 grams of Fe2O3 react with excess CO, what number of moles of iron? We don't need to do that one. We've done several of those already. How about 84? Oops. Here we go. Which of the following statements is always true concerning the reaction represented by the following equation? All right. 84. None of the statements are true. So this one is none are true. That means you have to look at all of them, right? If this is one of the possibilities, then you've got to search all four of the others in order to eliminate this one as a possibility. If we find any one of these statements true, then A is false. So let's look. B, if we have an equal number of moles of C2H6 and O2, there is no limiting reactant. Equal number of moles, these are not ratioed equally. 2 moles of that reaction, 7 moles of that. If there's equal, then one of them's going to run out. And oxygen will be the one to run out because you need more of them. So B is false. How about C? If we have equal masses of C2H6 and O2, there is no limiting reactant. All right. So in this case, we have to actually calculate the masses, the potential masses. If you have 2 moles of C2H6, what mass do you have? So 2 moles of C2H6 is equal to what molar mass? Or, well, 2 moles would be what mass? We need the molar mass of C2H6. So this is 24.02 plus 6.06, which is a 3008. So that's 60.16 grams for 2 moles of this. If that reacts with 7 moles of oxygen, what mass is that? Well, this is 32 grams per mole, right? So 7 times 32 is 224. Right? So go back to the question. If we have equal masses of these two, there's no limiting. That's not true. This ratio gives us different masses. So equal masses, one of them will run out. So this one is also false. How about D? If we have more mass of O2 than C2H6, must be the limiting reactant. We have more mass of O2. Well, no. If you have more mass of O2, it might be stoichiometric. That's not definitive. It doesn't say exactly if you have more mass of O2 that C2H6 must be limiting. It must not. Or it must. It just depends on how much. So we can't say that this one is true. That one is false. And the last one, if we have more mass of C2H6 than O2, must be limited. If we have more mass of C2H6, then O2 must be limiting. Yes. If we have more mass of this than that, say for this ratio, if we had 250 grams of this one, then oxygen would run out. So that was true. If you have more mass of C2H6 than you do of O2, then yes, O2 is limiting. And the only way to answer that question is to do this middle calculation. Okay, that was 84. That's it. That's all I have to review. Okay, this is Tuesday. Thursday will be an exam on this material. And let me see. Thursday. Here we go. Yes. Okay. Thursday, the 7th, will be the day of the exam, and I will open up Zoom and be here in case you have questions. If you take the exam at that time, then I'll be here. Either if you want to come in, physically take a paper exam, that's fine. Or if you want to take it at home during this exam time so that I'm here to help you if you have a question. Or you can take it by midnight on Thursday and you'll be on time. Okay, any questions? Practice, practice, practice. When you're presented with lots of problems like this, the best thing to do is just practice a lot of them. Okay, we'll see you.